It's a thrill, really, to have her here, and I'm so glad that she agreed to come. Carolyn Porco.
Nope.
Hello. Yes, thank you very much for having me. And I'm going to tell you this is going to be about as large a change in topic as you've ever seen. And I think that there's a little bit of a problem with this screen. So what should we do? Okay, time out. Can you turn the sound off? The offset. Anyway, I'm going to begin by telling you a remarkable and uplifting story about the inhabitants of a small and rocky, ocean-covered little world in orbit around an ordinary star among hundreds of billions of stars in an ordinary galaxy in a universe filled with hundreds of billions of galaxies. And this story goes that these beings, with unbridled imagination and laughing at the idea of boundaries and refusing to accept limitations, over time developed the languages of mathematics and science, became skilled technologists, developed mastery over gravity, and eventually flung themselves and their machines off their home planet and, as they called it, into outer space. And they did this merely in response to an innate desire to explore and to learn about their cosmic neighborhood and to secure the future of their progeny and to seek the answers to questions that had vexed them and every generation of their ancestors before them. How is it that their small planet and they living on it came to be? And what was the great cosmic theater in which life on their planet had unfolded? Well, of course, this is a story about us. And we humans now have been interplanetary travelers for over 50 years. And in that time, we have been to every corner of the solar system. We have sent our robotic spacecraft to all the planets, all 8 of them. We have rendezvoused with comets. We have even landed our spacecraft on asteroids. We have, at this time, a spacecraft within a year of an historic encounter with Pluto and the Kuiper Belt that it resides in. And in what I regard as humanity's finest hour, we even set foot on our own moon. And each of these missions has told a story about scientific discovery, extreme exploration, the thrill of adventure, and is part of a much bigger cosmic quest to come to have a sense or understanding of our own beginnings and to come to a sense of our cosmic place. They have also told a story about the search for meaning. A major chapter in the story, which is right now within a few years of finally drawing to a close, opened some 24 years ago when an expedition to return to the planet Saturn, a mission called Cassini, was finally begun. And it was a joint venture, it still is, a joint venture between the United States and Europe. And from its conception, it called for a complete, in-depth examination of everything in the Saturn system, the planet itself, its magnetic field, its enormous ring system, and its collection of many, many moons. And it's hard for me to believe that we are now in our 10th year of being in orbit at Saturn. And I'm going to be taking you in the next hour on a visual tour of the highlights of what we found around Saturn. There's not a prayer that I could tell you everything that we have found, because it'll fill libraries. But you're going to see just a few of the highlights with heavy emphasis on the images. I lead the imaging team on Cassini, so that's one of the reasons. But the images, of course, are what give us sight and what allow us a sense of immersion and engagement in an environment that we would otherwise only be able to either imagine or just see through a telescope. And then I'm going to conclude with what I think is the greatest legacy that this profoundly successful mission will leave behind once it's over. Now, Saturn is very, very far away. And Cassini at launch was very heavy. It was 6 metric tons. And even launching this spacecraft on the largest vehicle that we had in the American arsenal at that time, that was a Titan IV missile, even strapping solid rocket motors onto that missile and putting a Centaur upper stage on top of that, and then putting the spacecraft on top of that whole stack was not enough oomph to get it to Saturn in a reasonable amount of time, so it was looped around the inner solar system twice. It took 2 years. We encountered Venus twice. We encountered the Earth once. This was all for gravity assistance, so that the spacecraft could gain speed. And then, in a terribly poetic coincidence, on the eve of the year 2001, Cassini flew by the planet Jupiter for a final push to Saturn. Mm-hmm. Now, the object of this exercise is to get the spacecraft to its target as quickly as possible so that those of us who are involved in the mission are still alive by the time the spacecraft gets there. But that meant that by the time the spacecraft got there, it was absolutely screaming by, and we actually had to slow the spacecraft's acceleration down to allow it to get captured into orbit, which it did on July 1st, 2004, and that's artistically depicted here. More than half of the weight of the spacecraft, the mass of the spacecraft at launch, was fuel that was expended in this maneuver to finally get Cassini into orbit. It worked flawlessly, and so from there on began our orbital tour. And the tour is characterized by changing orbits. We have lots of targets in the Saturn system. We want to look at the equatorial and mid-latitude regions of the planet, and we want to visit the moons that reside in the equator plane. And then we also want to look down on the poles of the planets and the satellites, and also look at the rings. And so we use Titan, the largest moon, in fact, as our gravity assistance body, and then that way we change the orbit in a big way, we change its orientation, we crank it up and down. And this is what our trajectory has been through the Saturn system. And this allows us something that, of course, you don't get when you're just flying by, like the Voyager missions of the early 1980s. We can make a discovery of something and actually deem it so important that we change our plans and we go back and have second and third, in some cases many looks, and we have taken singular advantage of that capability. One of the main objectives of the Cassini mission, as I said, has been to study the planet itself, and in particular its meteorology. And in the past 10 years, we've learned a great deal about its wind speeds, the role of atmospheric eddies in energizing the jets that we find in the atmosphere, the life cycle of storms, and so on. But it just so happened, by coincidence, that we were present there with Cassini to see the eruption of a major storm on Saturn, the kind of storm that erupts only every 20 or 30 years, so this was really a blessing that it happened while we were there. And this is the largest storm that was ever seen by a spacecraft, but also the longest lasting storm. It was a big convective storm. It lasted for about 200 days. It produced lightning and electrostatic discharges that were picked up by various instruments on the spacecraft. And we got to see the birth, the development, and the death of it. And you're looking at this picture, you can see that the storm has developed and gone all the way around the planet. Finally came to an end. We're still studying this, and we hope and will almost certainly learn a great deal about it. But what we know now is that there was a tremendous amount of power that came out in the storm, enough to give us an inkling that these storms play a major role in the energy budget of the planet. And of course, this is all for understanding a bit about how our own planet works. So we stand to learn a great deal by having other planets to look at, so we don't look at the Earth, which is a very complex system, in isolation. As spring marched on into the northern hemisphere, because we arrived there at the height of southern summer, but as spring in the northern hemisphere arose and the darkness peeled back from the north, we were able to see this feature, which is the hexagon that was first seen by Voyager in the early 1980s, and we got a much better view of it now with Cassini. This is the feature that drives everybody crazy. Whenever we release anything about the hexagon and put it on our website, the spikes on our website go through the roof. I think it's because people must think it's got something to do with crystal energy on steroids or something, because it looks to everybody like a straight-sided figure, and we even have encouraged that, I guess, by calling it the hexagon, but it is really nothing mysterious. It is merely a jet stream with 6 very stable, very contiguous waves in it, and in that sense, it is no more different than the jets that we have on the Earth. Here is a look at a video that was created using data from our own Earth, our own jet stream, and you can see how irregular our jet stream is, but it too has roughly 6 waves in it, sometimes 5, sometimes 7. The reason why it's so discontinuous and irregular looking is because of the same reasons why all the atmospheric systems we see on the giant planets look more stable. The Great Red Spot has been there for hundreds of years. It's a giant cyclone, but yet it stays there. It's because on Earth, atmospheric systems pass over hill and dale and ocean and mountains and so on, and that creates friction and runs systems down. But other than that, the hexagon is really Saturn's jet stream. Of course, one of the best jobs I have as the leader of the imaging team is to produce really beautiful images, and I really got a lot of joy out of producing this one. I hope you can see it. It looks kind of dark. Can you see that well?
Yeah.
It looks like the screen needs to be brightened, but this is the vortex. It's in false color deliberately. We use false color to see different levels in the atmosphere. But it is the vortex that sits at the center of the hexagon. The hexagon's about 2 Earths across. This is about half the size of the US. The winds blow in this vortex 50% faster than the winds that leveled Moore, Oklahoma a few years ago. So it is basically a hurricane, and my team members, of course, are still studying it now. So lots to be learned about atmospheres in general and how they even relate to our own by studying what we found at Saturn. The rings, of course, it's a shame this is falling off the screen, but anyway, the rings are what makes Saturn the icon among planets that it is. They are a tremendous visual spectacle. They're 280,000 kilometers across, which means it takes light, the fastest thing you know, nearly a second. Someone's fallen off their chair. It takes light nearly a second to cross the rings. And in that, being that big, they fit just nicely between the Earth and the Moon. And they consist of countless icy bodies composed mostly of water ice, ranging in size from the tiniest talcum powder-sized particles all the way to the sizes of small apartment buildings. And they speed around Saturn at something like 20 to 40,000 miles per hour, but they only very gently nudge each other. They're what physicists call an equilibrated system, and any violent collisions in this system died out a very long time ago. So for that reason, they are paper thin. You are looking at edge-on at the rings here, and in fact, the thickness here is the limit of resolution in the cameras. They're even thinner than this. They would take up in vertical dimension, they'd be no thicker than this room. They are very, very thin because, as I said, they're very equilibrated. And they trace out the plane of gravitational equilibrium around the planet. And bear in mind that despite their physical size, if you took all the mass in Saturn's rings and you recomposed it into a moon of the proper density for the Saturn system, you would get a moon no bigger than this guy here, which is Enceladus. So, great big spectacle for comparatively little mass. And just to orient you, these are the shadows of the rings cast on the northern winter hemisphere of the planet. The processes that are ongoing in Saturn's rings today are believed to have occurred in the disk of solids and gaseous material that ultimately became our solar system, depicted here in an artist's rendition, in similar disks that we are discovering around stars today throughout our galaxy, and then reaching 1 trillion times larger in size. This processes we see in Saturn's rings are ongoing in the pinwheels of stars and gas that we call the spiral galaxies. So there's a great deal to be learned in studying Saturn's rings about the very early stages in the formation of planets and disk systems throughout the cosmos, which of course is one of the reasons why we're so intently interested in them. The rings exhibit a very large array of structures. You're looking here at a picture that was taken on approach before we got into orbit. The tiniest features, the very narrowest features you see here are only about 15 kilometers wide. Let me orient you because the names went off the screen. This is the most massive of Saturn's rings. It's the B ring. Most of the structures that are in the ring are self-formed, and so we've gotten a great insights into what causes those structures with Cassini. This is the A ring. It's not as thick or as massive as the B ring. Almost every single feature in here is driven by an orbiting moon. Gravitational interactions between the moon and the ring particles, I'll show you some of those. And this is the C ring. It's the most transparent of all. And this here is the Cassini division. I'm going to show you next region near the outer edge of the A ring. Now the orbit insertion brought us closer to the rings than we had ever been with Voyager, and closer than we've been yet on the Cassini mission. We flew only a few tens of thousands of kilometers above the rings as the spacecraft glided over them after getting into orbit. We flew over the dark side of the rings. And once the maneuver was over, we were allowed, the scientists were allowed, to take the spacecraft, point the remote sensing instruments down on the rings, and my team took pictures as we glided along, and they were astonishing for the kinds of information they gave us, the kinds of information we really wanted to see. And here's just some of the things we saw. Okay, this is a little bit of a shame here. This is a density wave. You can see more of it if it didn't go off the screen. This is a place where an orbiting moon has excited eccentricity in the orbits of the ring particles, and then they get phased in such a way as to lead to these very coherent structures where in some places the particles are really compressed together, and in other places they're not so much. So if you followed one of these dark bands around the planet, it would form a spiral. They are the kissing cousins of the spiral arms that we see in the spiral galaxies. This is the vertical equivalent of a density wave, spiral density wave. This is like a ripple on a pond, and it's caused by an orbiting moon that happens to have an inclined orbit relative to the ring, so there's a component of gravity drawing the ring particle out of the ring plane, and again, those inclined orbits are arranged in such a way as to lead to a coherent pattern. If you followed one of these crests, it too would spiral around the planet. So lots of features like this that are created by the actions of orbiting moons. By the way, the size of this picture is something like 200 kilometers across. So we've also seen some dramatic features created by moons embedded in the rings. Here is the outer edge of the A-ring. This is the Keeler gap. It's only about 40 kilometers wide, and it is created by this moon that we discovered with Cassini. It's called Daphnis. You can't see it, but it is 8 kilometers across, and it creates waves in the edges of its gap, again, because it's exciting the eccentricities of the ring particles. So we've seen lots of these kinds of things too. And these observations and many, many others would have been a gracious plenty for any self-respecting ring scientists, as they tell us a lot about the kinds of interactions between moons and ring particles, and by studying those interactions we get information about how massive the rings are, how the particles collide, how elastic or inelastic they're not. I know this sounds all very nerdy, but we're interested in this because this is all the material from which the planets form too, so it gives us some idea of what parameters we need to put in our models if we're hoping to model planet formation. One event that we knew Cassini would witness while we were there and we knew would be the very best chance we would ever get to see the rings in 3 dimensions, was the exact moment when the sun traveling, as seen from Saturn of course, traveling from the south to the north passed through the ring plane. This was going to be equinox, and the sun would be shining for a period of time of 4 Earth days, almost exactly edge on to the rings, and the rings would go dark, except where there were protrusions above and below the ring plane. It was shallow. Sunlight would create shadows. And so we were eagerly anticipating this event, and it just turned out to be remarkable. We knew it would be good. It turned out to be extraordinary. This is a mosaic of images. There's something like 27 footprints in this mosaic. It took us about a month to do of that moment. And this is basically, you know, lights out on the rings. Sunlight, of course, is shining on the planet, reflecting off the planet, and then back onto the rings. That's why this area is bright. But we had to brighten this side of the rings by about a factor of 60 so that you could even see it in a picture like this. So this was basically equinox at Saturn, never had been observed up close by a spacecraft before. And now remember Daphnis and the Keeler Gap and the edge waves that it produced? Well, this is what we saw during the equinox. Here is Daphnis. It's casting a shadow. We find it has an inclined orbit, and because of its inclined orbit, it is taking the particles on the edge of this ring and drawing them out of the ring plane to create these mountainous waves of rubble. And these mountainous waves are some 1 to 2 miles high. So I ask you to imagine this. You are in a shuttlecraft, flying low over the rings of Saturn. From your vantage point, the rings would look like an infinite white sheet, almost going to infinity. Remember, they're only 30 feet thick. And you're flying along, and you come upon a wall of rubble 2 miles high. That has to go in a movie. Okay, so here's some more things that we learned during the equinox event. Now you're looking, you're stepping back. Here's the outer edge of the A-ring again. The Keeler Gap is that dark line. This is Saturn's F-ring. And you see lots of features that look like there's texture to the rings. Well, this surprised us. All of these are density waves. We didn't expect them really to have vertical extension, but they do. It just tells us the particles are so shoved together that they're drawn up and below the rings. This is a big bending wave. It's casting a big shadow. But look what we see here. At the outer edge of this inky gap here, we see this feature, and up close, this is what it looks like. These features, we call them propellers, and in fact, we have affectionately named them after famous aviators. This one is called Amelia Earhart, and it is created by a small moonlet, about a ½ kilometer in size, agitating the rings around it, creating a sheared out propeller-like feature that is casting a shadow. And we have seen dozens of these things. They've told us about a component of the rings that we had no prayer of knowing about until this event happened. And we've seen dozens, and we have inferred the presence of millions of them from those observations. And we've even been able to track some of these. And we watch them, of course, orbiting the rings, but they migrate outwards. Some of them migrate back inwards. And in doing this, they are mimicking the migratory motions that we have long believed that planets underwent as they were forming out of the protosolar nebula. So these observations have given us a window into a process that we believe happened in our solar system 4.5 billion years ago as the planets were forming. So obviously a very exciting result. On to moons now. Saturn is accompanied by a very large and diverse collection of moons. There's some 60 plus, I've lost count. The skies of Saturn are literally spangled with moons, and they range in size from a few kilometers across, I've shown you some of the smallest, to the size of the US. And it's the inner collection of Saturn's moons that orbit in a plane. They all orbit in the same direction. We believe that they're formed out of the nebula that surrounded Saturn in its early stages, and in that they all consist of the same material and so on. And so this nebula of materials is analogous to that from which the planets form. So our goals in studying the Saturn and exploring the satellites of Saturn were not only to do a survey to see if we could discover any that had escaped detection from the Earth, not only to come away with accurate measures of their sizes, their shapes, their compositions, their internal densities, and other physical characteristics, not only to understand the individual geological and thermal histories of each of them, but also to study the system as a whole with an eye towards testing our notions about the planetary processes that are involved in the formation of solar systems, both our own and those that we're discovering today. And that's exactly what we've been doing for the last 10 years. And in doing that, we have taken some outstanding images. It seems the most beautiful images are those with the moons and the rings. And I'd like to show you some of those. Bear in mind that our own moon is 3,500 kilometers in diameter, or about 60% the size of the US. So here we go. This is the moon Dione. It's a third the size of our moon, and this is a view of the winter hemisphere of Saturn, the blue winter hemisphere with the ring shadows. Just a beautiful image. This is Dione, again, seen against the face of Saturn from an equatorial position. You're looking at the edge of the rings here and the ring shadows. Here is Dione again at a much higher resolution, just showing the kind of structures we see on these crater bodies in the outer solar system. Icy, very icy ramparts. These satellites are made largely of water ice. Here is Tethys, a little bit smaller than Dione, sporting a nice big crater basin, or impact basin with the rings, the dark side of the rings in the background. Here is Hyperion. This is one of the strangest bodies we've seen. It's about 250 kilometers across, so it's like a quarter of the size of Tethys, a small body, looking very much like a sponge that was pulled out of the ocean. I don't have time to tell you why we know how it got that way, but maybe in the Q&A someone can ask me. And this is one of the pictures we took very early on that just, I mean, it just grabbed so many people because we knew we were just in for a feast for the next N years, however long we'd be allowed to be operating at Saturn. This is Mimas. It's about 400 kilometers across, seen against the shadow-draped northern hemisphere of Saturn soon after we got into orbit, and this is the ring. So you're looking up at the rings, seen against the face, the shadowed face of Saturn. And here is Mimas up close. Okay, this is our Death Star. And the projectile that created this crater, Herschel crater, came very close to smashing Mimas to bits. So it doesn't take a rocket scientist to figure out that there must have been moons that did get smashed to bits. And that is, in fact, one of the cardinal ideas for how rings come about, that there was a moon in orbit around Saturn that got smashed up, maybe by a projectile coming from external to the Saturn system, maybe from the Kuiper belt, or maybe just moons colliding in the Saturn system early on, created debris, and that debris, just following laws of physics, conservation of angular momentum, loss of energy, would settle down into a ring system. And so the rings are continuing to receive a lot of attention because we're very interested to know how they came about. But the two moons that around Saturn that are really the standouts are Titan, which is Saturn's largest moon. It's 50% larger than our own moon, and until Cassini got there, was the largest single expanse of unexplored terrain that we have remaining in our solar system. That's just an indication of how far we've come in 50 plus years. And then Enceladus, which is a tenth the size of Titan, and it's a small icy body. Now, we learned from the Voyager mission to the outer solar system in the early 1980s that Titan's atmosphere was actually very similar to the Earth's. It's largely molecular nitrogen. The pressure at the surface is comparable to the pressure we have here. In fact, it's some 50% greater. It has a similar thermal structure. It has a troposphere, a stratosphere, a mesosphere, and so on. But it's different in some very important ways. It, first of all, has no free oxygen, and it is suffused with small amounts of organic materials like methane and ethane and propane. And it is these compounds in the upper atmosphere, they get broken up, and the carbon from them creates haze particles that make this 200-kilometer thick envelope of haze, that orange haze that envelops Titan and makes impossible to see down to the surface in the visible. So it's very, very dark at the surface of Titan. High noon on Titan is as dark as deep Earth twilight is on the Earth. And it was believed, this is based on the results returned by the Voyager mission, it was believed that over time, these haze particles might have drifted downwards, growing as they fell, to coat the icy surface of Titan in a blanket of organic sludge. And some of these compounds, it was realized, methane in particular, were expected to be liquid in the surface environment of Titan. In fact, methane is to Titan what water is to the Earth. It can be there present as a solid, a liquid, or a gas, just depending how you tweak the temperature. You're talking about exactly on the surface, in the atmosphere, and so on. And this is despite the fact that the surface temperature on Titan is some minus 185 degrees Celsius, rather cold. And this, of course, opened up a world of bizarre possibilities. You could have patchy methane clouds floating above an icy, sludge-covered ground. In places, you might have gentle rains of liquid methane falling down to the surface, cutting gullies, forming rivers and cataracts, carving canyons, washing sludge off the high mountain peaks and into basins, filling craters and low-lying depressions with liquids and so on. So stop and imagine, I ask you, to think about what it might be like. You are standing on the surface of the moon in the outer solar system. You are, of course, properly attired. It's dark. It's very, very eerie. It's extremely cold. It's misty. There is a light methane rain washing over you, and before you lies Lake Michigan brimming with paint thinner. Well, that is what we scientists thought might lie beneath the haze on Titan. We expected to find bodies of liquid methane all over the place, and we were very eager to find out if we were correct. And for this reason, Cassini was deliberately equipped with instruments that could see down through the haze, which is something that Voyager couldn't do. Two instruments in particular. One, Cassini carries a radar instrument, which is the same kind of instrument that was carried to Venus on the Magellan spacecraft and has no trouble whatsoever seeing down to the surface. You shower the surface with long wavelength radar wavelengths, and you intercept the reflected the electromagnetic radiation being reflected from the surface, and you transmit that information down to the ground, and it gets composed into a two-dimensional image. This is called synthetic aperture radar. And then, of course, my instrument carried special filters, which we learned could be used to see down to the surface. We needed to know that you had to look in the infrared, not in the regions where your eyes see. And so we did that, and we've been able to discover quite a lot because of the capabilities we've given Cassini. To show you what properly equipping your spacecraft does for you, here's a comparison, again, half off the screen, of Titan seen in the visible. This is the way it looked to Voyager. This is the way it looks if we on Cassini look with the red, green, and blue filters. But this is what happens when you look a little bit into the near infrared. In fact, with the same wavelength that is used by your television remote, we can see down to the surface. And this is typical of what we saw soon after we got into orbit. Very ambiguous. We couldn't make heads or tails of this. You don't see any craters. There's no sunlight on the surface, so we couldn't use the tools that we've used for 5 decades now in looking at airless bodies. If you know the angle of the sun, and you can see the length of a shadow, you can measure how tall the thing is, or maybe how deep the crater is. We could do none of that. We saw dark and light. In some cases, we saw traces of sinuous channels. We thought maybe those were, rivers or something, but we were very, very puzzled at what we saw. And then, of course, came a part of the mission that we all highly anticipated would be like the Rosetta Stone for understanding Titan. This was the deployment of the Huygens probe, which was an aerodynamically shaped device that carried 6 instruments, and it was deployed to Titan, and it drifted down from the mothership, and it drifted down through the atmosphere for 2.5 hours on a piece of fabric, and came to permanent rest in the equatorial region of of Titan. And I have to say, I just have to insert here, this was, for me, I was at the European Space Operations Center in Darmstadt, Germany, where this part of the mission was monitored because, in fact, it was the Europeans who built and operated the Huygens probe. I didn't have to do anything. I was just a guest, which was great. It was, you know, I'm living in one universe, one moment, and then after this thing lands, humankind have landed something of their own making on a moon in the outer solar system, 10 times farther away from the sun than the Earth, and then suddenly I'm in a different universe. The solar system felt like it got a whole lot smaller because of this event, and it was glorious. The probe had cameras, and it spun as it fell, so it took panoramic images, and it was very hard. It is hard to describe what it was like to see these images for the first time. This is some of them. They're here mosaicked, they're put into a mosaic, and it looks for all the world like a shoreline. And you can see an unambiguous drainage pattern that starts from about here and drains off the coastline here. These pictures were everything that our pictures from orbit were not. They were just completely unambiguous about the presence of flowing liquid. Then finally the probe landed on the surface, and this is a composite of images taken on the surface. You're looking close to your feet, and then 2 more images out to the horizon. So this is the horizon. This is near the spacecraft. These cobbles are about this big. And this was landfall in the outer solar system. We've learned a lot about the surface of Titan from the Huygens probe. We have found that the probe landed in the Titan equivalent of a mudflat. This is an unconsolidated ground, maybe, very likely, formed from the accumulation of organic material over God knows how long, we don't really know, millions of years, hundreds of thousands, of sludge off the high mountain peaks, or the high regions into the low regions. It was suffused with liquid methane, so there was a river here at one point, or maybe rain caused the ground to absorb methane. So this was very exciting, but there were no bodies of fluid like we expected. In fact, one of the instruments on Cassini, on Huygens, was an instrument that was to measure the properties of liquid should the probe land in it, and it did not. So, very exciting, but we're all worried. Where are the bodies of liquid methane that we expected to be there? And things got even more puzzling when the radar instrument that I told you about found dunes. This is miles and miles, thousands of miles, all the way around the equatorial and mid-latitude regions of Titan, are regions of dunes. Wherever we see the dark regions from orbit, looking up close, we see these dunes. They're longitudinal dunes. They're oriented in the direction of the wind. It takes steady bidirectional winds to form them. You have to have also dry particles to be lofted to create dunes. It takes a long time, hundreds of thousands of years to form these things. So this was a fantastic discovery. It looks so much like things we see on the Earth that made us think Titan was Earth-like, but there's no bodies of liquid. And it remained puzzling until finally we got the opportunity to look poleward. This happened about June, about a year after we got into orbit. This is the exact South Pole. This is a complex of methane clouds. And this is a feature that came closest to being like a lake that we had seen at that point. This is my team, we were so convinced this was a lake, or at least a lake bed, that we called it Lake Ontario. And then finally, we got to look in the northern regions, and the radar instrument, as I said, has no trouble seeing down at the surface. And they did an excellent job of mapping the places on the planet where there are liquid. And here's a region of a lake in the northern, a lake in the northern region of Titan, showing, it looks like the coast of Maine. You have channels leading into this body. We know now that it's filled with liquid methane. So we had the idea right. It just turns out that all the fluids have gone to the poles. This is a radar map. This is false color, by the way. This is the North Pole. This is 50 degrees latitude, so I think this would be the equivalent of either between Edmonton and Calgary, or maybe as far south as Calgary. So this whole region is from there northward. And these are bodies of liquid methane. This body here, which is in fact connected, if you scaled up Titan to the size of the Earth, this would be the size of the Mediterranean. So there's 10 times, at least 10 times more fluid in the north than the south, and there could be much more than that. We don't know why that's the case. And here's just a glorious image taken in the infrared showing a glint off the northern seas of Titan. So it's not clear to us exactly what's going on, but one thing is very clear, that after decades of speculating what might lie beneath the haze on this very mysterious moon, we now know, and we have found an utterly remarkable place, a place which is the only place in the solar system where we have abundant liquid hydrocarbons ponded on the surface, a place that is both exotic and alien and yet familiar all at the same time, and a place that in all the solar system, in its complexity and in its geographical diversity, is rivaled only by the Earth itself. So we remain fascinated by Titan, and hopefully we will get our extended mission to go on 4 more years, and if so, then we intend to do a lot more exploring of Titan. But now we come to what I think is the most thrilling and most profound discovery that Cassini has made, and that is what we have found capping the south polar region of the small moon Enceladus. This is a picture that we took early on of Enceladus, shown alongside Great Britain, so you see its relative size. This is not meant to be a threat. And this is about the resolution of the images we had with Voyager. And in Voyager, we thought that there were vast tracts of this moon that were completely smooth. And when you see the cratering record completely eradicated like that, it tells you that the moon has been internally active. That's the only process. If you have an airless body with no atmosphere, that's the only process that could just destroy craters and make for smooth areas. So we knew that Enceladus was different. It had been internally active, but it's small, and we couldn't figure out how it got that way. Very puzzling. We also know that it was situated in the middle of one of Saturn's largest rings called the E ring, a donut-shaped, very diffuse ring made of only very small particles, like the smoke-sized particles. So we figured it could be internally active. It certainly was internally active in the past. But when we got there with Cassini, as often happens when you go back with finer instrumentation, better resolution, more sophistication, what we found was we were entirely wrong. Okay, the body is crisscrossed by multiple generations of tectonic fractures. It has deep chasms, it has mountain belts and folds and so on. Very few craters, so this tells us it's a very young surface. It's been geologically active in the recent past. But far away, the mother lode of discoveries that we have made on Enceladus are found at the South Pole. This is exactly where the exact South Pole is, and this whole region, again, at about 55 degrees south latitude, that's just a coincidence, is circumscribed by a mountain belt. So it's very geologically unique. It's characterized by these 4 main fractures. They're about 135 kilometers long, 35 kilometers separated, they're only a few kilometers wide, and about 300 meters deep. This is a very false color image. To your eye, Enceladus would look pure white. It's the whitest object in the solar system. It's also the brightest object in the solar system. I should say here, this is another picture we took near equinox, which is why half of the polar region now is in darkness, giving you a much better look at the mountain belts that encircle this very unusual, unique region. When the instrument on Cassini that can measure thermal radiation and can figure out how hot something is, looked at the south polar region of Enceladus, it found that there was lots and lots of heat coming out of these fractures. Okay, so the whole thing was just puzzling to us. When we took pictures where the south polar terrain was on the limb of the planet, the moon, so we could take a picture looking back in the direction of the sun with this region on the limb, this is what we saw. There are dozens of jets of fine icy water ice particles that erupt from the south polar terrain, and when you take a picture like this and you color code the very faint gray light levels so you can see them better, this is what you see. These jets form a plume of material, and in fact, some of this plume escapes the gravity of Enceladus and goes into orbit around Saturn, forming the ring that we have known since the 1960s was there. So the E-ring of Saturn is actually formed by these eruptions on Enceladus. Now, Cassini has flown. After we made this discovery, this is one of those examples where we altered our plans, like stop the presses.
Yeah.
We have to go back and take a closer look at this. We have flown Cassini now through the plume several times. There are instruments on board that can pick up material and measure the composition. If it's gaseous, one instrument can do it. If it's particulate material, another instrument can. And we have found by doing that that these icy particles are salty. They have the same salinity as, comparable to the salinity of the Earth's oceans, and they are accompanied by water vapor and trace amounts of simple organic molecules like methane and so on, and even a small amount of ammonia, which has nitrogen and carbon dioxide, all of the compounds that are considered important for the origin of life. And the analysis of all this information together, as well as the addition of images like these. This is a very high resolution image we took of the jets showing how they are oriented along, or they're aligned along the fractures. Here's one we took later on when the shadow of Enceladus was creeping up the jets as the south was falling into winter. Here is another image. I love this image. This is looking over the limb of Enceladus in the direction of Saturn. Baghdad and Damascus are the names of two of the fractures. You can see the feet of these jets. So you take all these images together, and this is done in my group. This is actually my research. I'm very proud of it, so I'm going to boast. I'm going to boast like crazy. We have taken this and we have used these images and others like it to survey the South Pole, just like a terrestrial geologist would survey something to figure out what its coordinates were. We did that, and we formed this map. We find now 100 jets, and they all align along these fractures. Okay, and we have enough information that we can pull out their three-dimensional configuration, and we can see that they are pretty much erupting perpendicular to the surface. Some of them are very tilted. But anyway, all this information that's been gathered over the last 10 years, I'm skipping something. I should say another matter of great importance is that, as I told you, the infrared instrument found that there's lots of heat coming out of the fractures. Well, when that instrument gets really high resolution, looks at the fractures, it finds that the heat is really coming out in little spots. And within my group, we have shown that those fine spots are actually the thermal signature of individual jets. Okay, and we've been able to deduce from this that the heat coming out is not created now. It's not, friction in the fractures because Enceladus is being flexed in a resonance, which it is. It's really the heat that comes when water, vapor, and some liquid condenses out and it releases latent heat, and then that latent heat can be conducted up to the surface where the Cassini instrument can measure it. So all of this stuff together has told us that these jets are actually geysers, and they are erupting from pockets of liquid water. And most recently, a report from another team on Cassini that tracks the spacecraft, and by tracking it can tell how much mass there is in the satellite and how its mass is distributed. They have come to the conclusion, they've actually confirmed what we've thought now for 10 years, that there is a liquid sea under the ice shell that forms the south polar terrain of Enceladus. And it's at least as wide as the south polar terrain is. It might even be a global ocean. So all of this together tells us that Enceladus presents to us today not only an environment of excess warmth and organic materials, but one where there's salty liquid water present, which means the water is in contact with a rocky core. And in other words, an environment where prebiotic chemistry and perhaps, and big emphasis on the perhaps, even life itself may be stirring. And so we are like drunk on this, and if we are correct, it is not completely crazy that we could have microbes snowing on the south pole of Enceladus. Cassini, unfortunately, is not equipped to answer the question as to whether or not we have extraterrestrial life on this moon, but I don't think I need to state it too strongly that should we ever find that life has arisen independently twice in our solar system, that is, if we could find evidence for a second genesis in our solar system, then at that point, that means the spell has been broken, the existence theorem has been proven, and we could safely infer from that that life was commonplace, that it was not a bug, but a feature of the universe in which we live, and it had occurred a staggering number of times in the 13.7 billion year history of the universe. And I think you would agree that that would be a final answer to probably the longest standing question in human history, and the kind of discovery that could change a great many things. And because of all the thrills and the excitement that this moon has afforded us, I am personally holding on to one fanciful notion, and that is that someday in our far future, our distant descendants might voyage back to the Saturn system to visit the Enceladus interplanetary geyser park in a spaceship not unlike the Starship Enterprise. And I want to put a plug in here that there are some of us, a small group of us scientists, despite the situation with NASA's budget and so on, we are very much hoping that we could conduct a mission back to Enceladus that is properly equipped to investigate the astrobiological potential of this environment that we have found. And we are hoping to actually have a component of that mission be a sample return. We send a spacecraft out there, we fly through it, and a component of that spacecraft actually comes back to Earth. 7 years out, 7 years back. You have to be patient when you study the outer space. So anyway, Cassini continues as I speak to orbit Saturn and return one discovery after another and deep insights into how our cosmic neighborhood came to be. And when it is all done, I think it will go down in history as one of the most scientifically productive planetary missions that NASA has ever flown. But in the end, the story of Cassini, like the story of all our interplanetary explorations over the last 50 years, has been a story of a longing to know us, a longing to understand ourselves. And despite all the glorious images that I've just shown you, despite the spectacular vistas that we've been treated to over the last 10 years, there is one image that says this, I think, better than images or words ever could. And it has a bit of a backstory, and so I want to tell that to you now, and I'm terribly late. Is that okay? Am I going to get dragged off the stage?
Okay.
Okay, so back in the 1980s, I was a young graduate out of graduate school. I graduated from Caltech in Pasadena, and I found myself hitching a ride on one of the greatest scientific adventures of exploration ever, and that was the Voyager mission to the outer solar system. And in that role, I had the pleasure of coming to know and to work with Carl Sagan. And I worked with him and others in planning and executing what is now the very famous Voyager pale blue dot picture of Earth that was taken of the Earth by Voyager 1 in 1990 when it was out past the orbit of Neptune. And it's not well known, but as Carl had described it in a proposal to the Voyager project to take this, this picture, which incidentally was denied, and he had to go all the way to the NASA administrator to get JPL directed to take the picture. The idea was to take a picture of Earth, and I quote, awash in a sea of stars. Now the actual pale blue dot picture, many of you may remember, was not really what we had envisioned. There are no stars, and the Earth is sitting on top of a beam of light that in fact was caused by scattering of sunlight in the optics of the camera. So maybe not, photographically or compositionally as spectacular an image as we had hoped, but none of that, of course, really mattered, because it was what Carl had to say about this image and the way that he romanced it and the way that he turned it into an allegory on the human condition that has forever since made the phrase pale blue dot synonymous with an inspirational call to protection of the earth and the environment and to planetary brotherhood. Well, ever since the very beginning of my tenure as the leader of the imaging team on Cassini, I have had in the back of my mind to do this picture over again, only make it better. And it occurred to me some few years ago as I was with my group looking through the plans to see was there any opportunity where we could take this picture without disturbing my scientific colleagues from all the things they wanted to do. It occurred to me how great it would be if instead of taking the picture and then showing it to the world, like I should add, lots of other missions have done since this original picture. It's almost now de rigueur for missions to take pictures of Earth and then some day or 2 weeks later say to the people of the world, look at this picture we took of you from, you know, the surface of Mars or something. I thought, wow, what a missed opportunity. Why don't we tell the people of the world ahead of time, at such and such a time, your picture is going to be taken from the orbit of Saturn. Go out, contemplate at that moment, contemplate the utter isolation of our planet in the blackness of space. Think about its life-giving beauty and the rarity that it is among planets. Marvel at your own existence and all of life on Earth. And so it happened. On July 19 of last year, the Cassini cameras were turned to look back at Saturn as it eclipsed the sun to take another pale blue dot image of Earth, and we sent out the word ahead of time. At the moment the picture is taken, go out, look up, think of all of us together on planet Earth. Think of the magnificent achievement that this interplanetary salute between robot and maker represents, and smile. And people responded just exactly the way I had hoped. Many comments came in from people all over the world stating a feeling of unity with their fellow humans. And here are just a few, I want to read them to you. Richard from Pennsylvania. What a great way to feel connected to the universe, the planet, and every single person on it. We really, truly are in this together. Bill from somewhere. I looked up to the sky with a glass of Arbor malt whiskey and reminded myself how lucky I am to be alive. Wayne in England. I drove for an hour with my son to witness the event from the Stone Circle at Avebury in the UK, joined by many others already there. What struck me most was the fact that we were standing on one human artifact created over 4,000 years ago, looking at another 1 billion miles away. Though separated by vast distances in both time and space, they each represent what humans can achieve if we apply ourselves. Chris from Iceland. I was in Reykjavik. We went down to the waterfront and threw a wave in the general upward direction. Tess from somewhere. At the appropriate time, I left the table at a restaurant and I went to the parking lot. I turned my face to the sky and I spent a few minutes watching and listening to what life on Earth was like right there, right at that moment. What a feeling of connection and oneness with the miracle that is life on Earth. This experience was beyond meaningful. It was transcendent. What a beautiful thing. And then here's one of my favorites. Jolene from upstate New York. I've been entranced by this project ever since I heard about it and was determined to join in the celebration. However, I never anticipated how emotional I would feel. I stood on the edge of Lake Ontario in upstate New York with my son and his girlfriend. I forgot to bring my cell phone with its app that shows the location of Saturn, so in the end, we just spun in circles waving at the sky. The thought that a camera was taking pictures from so very far away was just incredible. We may not be unique. We may be transient. We may be only flying along on a dust mote, but darn it, for 15 minutes, we were there, we were aware, and we smiled. And so the whole thing was a great success, and here now is the mosaic that was taken as these people and many, many more were thinking about our cosmic place, a picture that I called The Day the Earth Smiled. And it shows the E-ring that is created by the spray coming off Enceladus, which unfortunately is off the screen. This is the moon Tethys. You saw Tethys. The sun is behind Saturn. You're seeing the main rings of Saturn illuminated in silhouette, as it were. And if you look over the shoulder of Saturn, in the distance, 1 billion miles in the distance, is our little planet Earth. And as we get closer with our narrow angle camera, we actually, for the first time from the outer solar system, capture the Earth and the moon.
Oh, wow.
So there is, I think you would agree, something very powerful that we feel when we see our own little fragile blue ocean planet as it would be seen in the skies of other worlds. And I think it is that startling, uncorrupted recognition of what we really are, as we really are, that never fails to move us. And it moves me too, and it moves me to think about evolution. In fact, for me, this is the picture where Charles Darwin and Galileo come face to face. Because it is a picture that was ultimately made possible by Galileo's first experiments with gravitation 400 years ago, and it is a picture that positively shouts evolution. I look at this picture and I see our distant ancestors stepping down from the trees and walking upright for the first time onto the African savannas and pausing to look back at the forest from which they came. And I look at this picture and I see a species that is positively, absolutely unyielding in its pursuit of knowledge, and brave and fervent in its longing to grasp the meaning and the significance of its own existence. And finally, I can't help but look at this picture and see the very, very best that humanity has to offer. We are reminded day in and day out that we are the small and troubled and cruel and warlike inhabitants of one tiny little dot of a planet. But it serves us well to remember that we are also the thinkers, the dreamers, and explorers who took this picture. One world clear across interplanetary space to another. And to be so small and reach so far is, in the end, what makes us the extraordinary citizens of planet Earth. And there is sufficient spiritual nourishment in that to last all of human existence. I thank you.
And there's no worry, they'll hold lunch for us, so don't worry about that. The buffet's not going anywhere. So feel free to come on up to the mic if you have a question, and do some Q&A for a while. Oh, they'll do one there in a second.
And allow me to, oh, it's off the screen. Okay.
Lunch anyway.
Hi. I'm just wondering if there's been any plans to send a probe or a rover to Enceladus. I know it's like fairly recent discovery with the water.
Well, I would dearly love it if NASA would make it such a high priority that we would do it tomorrow, but that's not going to happen. So the moon that is the next on the docket that will have the next big mission sent to it will be Europa, which is a moon of Jupiter, which is also believed to have an ocean, but it doesn't have the accessibility that Enceladus does because of, and it hasn't been studied as much as Enceladus. So some of us think that Enceladus is the best bet. And that's why a group of us are trying to put together plans for a mission to go back. But, you know, I don't think it takes a lot of work to do this. We're having to get the Japanese to cooperate with us because no one nation can do this alone anymore. The missions are getting much more expensive because we want to do more sophisticated things. So the answer is yes, but not in an official sense. You know, NASA hasn't said, Enceladus is a high priority, we're going to do it, you know, next. At least as far as I know, that hasn't happened. Europa would be the next big mission.
Sorry, just one more question also. Thank you. You mentioned something that would be ideal to be able to capture a sample, a collector of the water coming from Enceladus. What about gathering a sample or a collection of the ice that is around Saturn? Is it possible to send a probe through there and get a collection to actually bring it back to Earth?
Yes, but that would be, we think, less astrobiologically productive because we think the particles that have all the interesting stuff are the bigger particles, and actually 96% of that stuff that goes up actually snows back down. Only about 4 to 5%, and it's just the very, very tiniest particles make it into orbit around the E-ring. And we don't think those are, in fact, we've captured some of those with Cassini and measured them. They don't have salt. If they don't have salt, that tells us they're probably not from the interesting region. So they might be just water vapor that condensed out once it hit the vacuum of space. So the place to go is as close to the surface as possible where we can pick up the bigger particles, which are not very big, but they're the ones that we think are the interesting ones.
Excellent. Thanks very much.
I guess I've got a few questions, but I'll start with the one about Enceladus. Take the picture back to the one where you're showing this map of the South Pole area.
Okay, let's see how this works. The map with my jet locations on it?
Yeah, the jet locations and the coordinates.
Don't you like this one?
Yeah. Yeah.
That was my scene in Star Trek. I'm not kidding.
Okay.
No, not, you mean this?
Okay, okay, that's interesting. Now, 0 is towards Saturn.
Yes.
Yes. Okay, so.
Oh, I'm in
okay,
trouble now.
okay, so I was kind of expecting the stripes to be oriented toward the Voyager side, but it's interesting that it's 45 degrees.
Well, no, that's the place of greatest stress.
Yeah.
The 45-degree line is actually the place of greatest stress.
So, do you think it's just chance that it's not 45 the other way?
What do you mean? It's 40? Of course, it's 45 the other way.
Okay.
This is 45 degrees. This is the line, so
Yeah.
the whole thing can't be 45.
Yeah. You can't.
Oh, the other way.
Yeah.
No, I think this is what happens when you get a viscous lag. Do you really want to go into this here?
Okay.
Maybe we should do it, you know.
And I'll point out Calgary is 51 degrees north.
Oh, okay. Okay, very good. Okay, thank you. Yes.
Hi, thank you for the presentation. I was just wondering what your thoughts are on different projects like the Mars One project.
Is Mars One the plan to send people on a one-way trip to Mars? And this is being done by, remind me, who wants to do this?
I think it's just publicly funded by Mars One group.
Okay. Well, on the face of it, sounds crazy. But, you know, I'm a big one for needing a human flight program. And I would rather see it done in a little bit more systematic way because, I mean, I'm afraid a project like that is going to attract some loonies, and that might actually hurt the whole impression of it. But other than that, I don't have much more to say. I just want to see a vigorous human flight program. I want to see a vigorous presence in space. That's what I want to see. I think that's, that's where we have to be, and it will serve us well to do that.
Thank you. So it sounds like there's a lot of water up there. I was just wondering if...
Lots of water.
Yeah. Did the team find that surprising? Where did the water come from?
Oh, no. We've known for, as soon as we had spectroscopes that could, tell composition, we've known that there's lots of water in the, beyond the orbit of the asteroid belt, because that's the line where, the temperature decreases as you get further from the sun, and that's the place where water vapor would freeze out to make ice. And in fact, you get even further out, and things like methane freeze out. On Neptune, you can get methane ice particles. I say that because methane is more volatile than water, so that didn't surprise us at all.
Hi, thank you for putting the spin on Star Trek too, because I think it's a little bit more linked to humanism than I think you're a little with Star Wars. Bill, I think we should have a speaker related to astronomy every year. I think it's very much appreciated. I thank you for putting a positive spin on human potential in the end. But a few weeks ago I'm watching some TV and private enterprise kind of wanting to mine asteroids and sending people into outer space. And do you feel personally that as a species and as role models we are ready to go out there? Because I'm a bit, negative that we would be kind of spreading viral, unsustainable memes such as religion or capitalism out there, and we'd be more of a cancer to the universe. So what do you think? Are we evolved enough to really, present ourselves out there and be good role models?
Well, we're presenting ourselves out there in a big way through our electromagnetic signals that are going out there. You know that. So if there's a species out there that has a big old antenna that is, collecting I Love Lucy,
Like Rush Limbaugh, we're screwed.
Archie Bunker.
But do you think we're ready now, or would you like us, like maybe in 100 years, we'd be better role models to go out there? Or?
100 years? No.
No.
I think, I don't know how much will change in 100 years. I do think that eventually, I don't know if we should get into this, but I'm not too worried about it. Let me just say that. I don't think about that because, to actually venture beyond, humans, to venture beyond the solar system, like to go on a one-way trip and hope to colonize, way in the future, if ever, way in the future. I think it's realistic to think that we could have outposts on some of the planets the way that we had outposts, we developed outposts on Antarctica. That's a very good analogy, And, there'll be research outposts at first. You're not going to take 7 billion people, soon to be 11 billion people, and move them to Mars. Okay, you're not going to do that. That's not going to be what space exploration is going to be like, or space colonization. It's going to be more in the model of setting up outposts. So that's how I think.
So thank you. So it's a little bit early to worry about whether we'll have a positive or negative effect out there because we're still very limited in it.
I think so.
Thank you.
You don't need to lose any sleep.
Regarding the level and kind of education that a person needs to do the kind of work that you're doing and that your colleagues are doing, there's a lot of kind of doomsaying about the state of education in North America, and especially in the US. And with the kind of plans that you're advocating and that I think sound great, it seems you're going to need even more people than we presently have who are capable of this kind of thing. And do you see a negative trend in that maybe the next generation of scientists prepared to do this kind of work might be smaller or less able to collaborate with those in other countries?
I don't know that we need a whole lot more people to do it because there are a lot of people in my business who don't have jobs. The people eager to do this, the people already trained to do this don't match up with what's available to do. So I'm not worried about that. As far as the level of education, well, that's a problem. I don't have the answer to it, but we absolutely need across the globe, but certainly in the U.S. I don't know if you guys in Canada have a problem, but we have in the U.S. have a terrible problem with scientific literacy. I do see though that it's taking a turn for the better. That people are much more interested in science than they used to be. So I think that's good. Cosmos, how many people are watching Cosmos? It's getting a very respectable response, and I've been told that while the ratings went a little bit down, they seem to be going up again. So that's all very good that it's had such a great reception. And I bet you'll see more shows like that in the future. I bet more kids will be interested in science. So I have hope for that. Near term hope I have.
Thank you.
You're welcome.
First of all, I'd like to thank you for coming, and I absolutely see a relevance between the kind of issues that we're looking at and our exploration of space. One of the things I'm really curious about was the theory that the reason that no intelligent life had been discovered yet is that the same features of evolution that bring us to the point of discovering technologies that allow us to explore the outer universe are the same tendencies that cause us to self-destruct. And the theory that Sagan had and that others had, that within 100 years or 200 years that the likelihood of a species that discovered nuclear energy, for instance, would self-destruct are more than 99.9%. And that was one of the big explanations as to why there was no intelligent life discovered in the universe. I'd like to know what your thoughts are on that subject, and also whether I still believe that that's a likely outcome.
I don't know where the 99.9% came from, but it is true there's a yin and yang. You can take anything, music. You could use it for good, you could use it for bad. So it seems over time things have been getting better. You read Steve Pinker's book; he's a great optimist. You wouldn't believe there was anything really wrong globally anyway if you read his books. I mean, he uses real data, so I'm going to trust what he says. Remember, and I have to remind myself this too, when you turn CNN on or Fox News or whatever, you are getting the worst of the worst as far as news reporting goes. They do that because they want to hook you. We're all evolutionarily evolved to, worry about those things that might threaten us. So we see nothing but the bad. And, like I said to the previous speaker, I have hope in the near term. I think we're on a good trend, and we just have to keep going at it.
Yeah, other than climate change, the world has never been in such good, habitable shape. In reality, it's just that we're smothered with bad news. That's not what climate is.
Well, climate change is the thing that really, the one thing that really worries me.
That's the game changer.
That could be a game changer.
So my question is, and I'm the last one, so I'll see if I can find before it throws me out of here. Okay, first question: Why is manned or people space flight more important than, say, technical space flight with instruments?
I didn't say it was more important.
Or not more important, but
I just want to see it.
yeah.
Why do I want to see it? Well, humans can do things that machines can't.
Oh.
Think about that. It'll take many rovers to Mars, to pick up certain rocks. It might just take a whole day, maybe 2.5 days, and pick up a lot of rocks. Just compare what was returned from the Apollo missions in terms of rock samples. And also, it's just one of those undeniable truths that people at large, the lay public, identify more with seeing people than machines.
Yeah.
It's just the way it is. So I think
It's exciting. It's really exciting to see people.
It's exciting. It's inspirational because you see one of your kind absolutely doing something at the very limit. It's like watching a sports figure. Jump, whatever those things are, they jump. Like higher than anybody's ever done before. It inspires people, and we need inspiration. It's just, that's it.
The only drawback is that once we put human being into a spacecraft, it's just so enormously more expensive.
It is.
So we use a lot more budget.
I won't deny that, but NASA's budget is 0.5% of the federal budget. Okay, when you think about that, what's 0.5%? 0.5% is nothing.
The total advertising budget for cosmetics in the United States is more than NASA's entire budget.
Right, so it's not a lot of money.
So I got one question. Just don't. Okay. Does Saturn or do any of our other planets have iron cores and electromagnetic fields the way Earth does?
Saturn and Jupiter, and I guess Uranus and Neptune too, have rocky cores. Their magnetic fields derive not from iron fluid, which is what happens below us, but it's a metallic hydrogen. It's basically a plasma, a thick plasma that has currents in it, and it's magnetized material that, roiling around like that creates external magnetic fields. So that's where they're magnetic.
That deflects some of the, well, I guess up there, the sunlight's not a factor as far as...
Our magnetic field doesn't deflect sunlight, it deflects charged particles.
Charged particles.
Yeah.